Alright, so moving on, our next section, using partial factoring to sketch the graph of the quadratic. What we have here is we've got a function that we need to state the domain and the range for. So I look right away and I don't see anything that indicates I can factor this regular. And so this is kind of a special type of factoring that allows me to still plot out the graph in kind of a way that uses that symmetrical look of the quadratic the same way that we talked to it from before. So here's kind of the, if you want to call it a trick, here's kind of the trick for this thing. We're going to start, and I'm going to take a look at the first couple of terms. So minus x squared plus 6x plus 10, I'm just going to take a look here. The first two terms, what do they have in common? Well, they've got an x in common. Okay, so I'm going to factor out an x out of these terms. And really I'll take out the negative from there. So if I factor out a negative x, I have x minus 6 left over, plus 10. Now, what does this really tell me? Like, how did that help me move forward in this question? Well, our next step would really be to find the zeros, right? So we would say, when x is 0, what do I get for a value? And so, in this case, I'm going to treat these just like we did before, and we're going to try to find our roots and see what they give us. So before, what we would do is we would start to say, okay, let's find our functional values and see what they're going to work out to be. And maybe I'll just draw my lines over just to show this a little bit more clearly. So treat this like we would with the other one. We would say negative x equals 0, x is equal to 0. And then we treat this one the same way. We have x minus 6 equals 0, so x is equal to 6. But now what happens when we plug these values into our function? So when I plug f of 0 in, I'm going to have negative 0, and then 0 minus 6 plus 10. You kind of see that this is only going to work out to give me 10 as an answer, because this whole term is going to cancel out 0 times anything. And then if I do the same thing over again, and I plug 6 in this case, I'll have negative 6, and then we'll have 6 minus 6 plus 10. And 6 minus 6 gives me 0, so that means that f of 6 is also going to equal 10. So I'm getting the exact same answer for this. If I were to write these out as coordinate points, what this would show me is I'd have 0, 10, and then I'd have 6, 10. And that's really helpful because parabolas are so symmetrical. And so now if I wanted to plot this out, just to kind of get an idea of what it is that we've just done here, I'd have my x value, I'd have my function, and I can see that I'm going to have to go to 10 here. 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10. So if I were to start to plot this out, at 0, 10, I've got a point, and at 6, 10, I have the same point that's equally as high. So 1, 2, 3, 4, 5, 6, and way up here, I've got my other point. So then I can take a look between these 2 points, because I have this symmetry involved here, and we can figure out what the axis of symmetry is for it. So between 0 and 6, what's the halfway point? And so my halfway point here is 3. And so similar to before, what we did, if we wanted to, we could take, for your axis of symmetry, what we could do is we could add them together, remember, and divide by 2. And so that gives me my 3 for my axis of symmetry. So I know x is equal to 3 for this. If I plug 3 back into the equation, that's going to tell me what my vertex is. So let's plug 3 back into our equation. So f at 3 is equal to, and I'm just going to start right from the beginning, negative 3 squared plus 6 times 3 plus 10. So f at 3 is equal to negative 9 plus 18 plus 10, and f at 3 is equal to, and it looks like this thing is going to work out to be a fairly large value. I'm going to have 19 as a final value. So my axis of symmetry shows that my vertex is actually quite a bit higher, and so we're just doing a sketch. I'm just going to plot out kind of where that sketch value is. So if this graph kept going up, I'd have it way up here at 19, with my vertex being 3, 19. And then that shows me that this thing then opens down and comes down in both directions. So it just wants me to state the domain and the range for this thing. X is going to be in the set of real numbers. It includes all the values, and y is going to have to be less than my maximum point of 19. So if I write out my domain and my range, my domain is such that x is in the set of real numbers, and my range is such that y is less than or equal to 19, where y is in the set of real numbers. So it just helps me kind of visualize what this thing looks like. So I have another one for you guys to try, same as before. Apply the partial factoring strategy to locate 2 points. I have the same y coordinate on the following. So pause the video, give it a try, and come back when you're ready. So with this one now, I have my y value. Of going through the same kind of partial factoring strategy. So f of x is equal to, I'm going to factor out my x term to start, and then I'm going to write what's left over. So I'm grouping my first 2 terms together and partial factoring those out. So negative x comes out, I'll have x plus 3 left over, plus 12. This tells me that when I bring this out, and I do this one, remember it's negative x is equal to 0, so x is equal to 0, and then when I want to see what that gives me, remember if I plug 0 into my function, I'm just going to get 12 as a result on the side, because this whole factored term is going to cancel out. And then if I do the same thing over again, and I now take a look at this term, and see I've got x plus 3, and we're going to make it equal to 0, then x is equal to negative 3. So when I plug negative 3 into my function, I'm also getting 12 as an answer, because I'm canceling out my factored term. So after that, we're going to graph this out and kind of get an idea of where this thing would be. And so I have 2 values here at 12, and they're at 0 and negative 3. So 1, 2, 3, 4, 5, 6, 7, 8. Now this one's going to go up to 12, so I'm going to jump my f of x group by 2's. 2, 4, 6, 8, 10, 12, 14, 10, 12, 14. And so this one is just going to jump up by 2's, just so I can put everything in the graph. Which means also going below will go by negative 2 as well. So when f is 0, I'm at 12. And when f is at negative 3, I'm also at 12. I can see this is a negative value in terms of my factored form even, so I know that this thing is going to open downward. And so we just need to figure out, okay, what's the halfway point? Same as before. So we're going to take a look for an axis of symmetry. Okay, so axis of symmetry. Remember, we add up our 2 roots and we divide them by 2 so we can find the halfway point between here. So looks like 0 and negative 3, so 0 plus negative 3 divided by 2 is going to give me negative 1.5. So x is equal to negative 1.5 would be our axis of symmetry here. So 1.5 all the way through for our axis of symmetry. So now if I plug 1.5 back into our equation, f at negative 1.5 gives me negative 1.5, sorry, negative times the negative 1.5, I have to be careful with my brackets, negative, and everywhere there's an x I'm going to put in negative 1.5, negative 1.5 plus 3 plus 12. So f at negative 1.5 is going to be a negative times a negative is a positive, so that's 1.5. And then negative 1.5 plus 3 is positive 1.5, and then plus 12. So it looks like this thing's going to be 14.25. So way up top again, going through here, I'll have a value at 14.25, and this thing just opens going like this, going downward. So my domain and my range for this again, domain is such that x is in the set of all real numbers, so x includes everything, and then my range value has a restriction to it. So in this case, because I have a maximum, have a high value, remember I need to put everything below that. So y is going to be less than or equal to 14.25, such that y is in the set of all real numbers. It includes everything. So that's our partial factoring strategy. We have one more question to run through, and so that's determining the equation of a quadratic function. So if you're given the graph, to then be able to use the graph to figure out what the equation would look like. So I'll get you pause the video, give it a try, see if you can see how far you can get, and then come back when you're ready, and we'll go through the answer for it. So remember for this one that we have an equation that we started this whole unit with for factored form. So we have this equation. I'm going to go way back to what we wrote out from before. See our factored form here. Y is equal to a, x minus r, and x minus s. Let's set up that equation first. So y is equal to a, x minus r, x minus s. Now, identify where your roots are. Let's start to label some points on the graph here. Here's a root, and here's a root. Here's where they cross the x-axis. Happens at negative 1 and 4. So remember that when we put them back in, we have to make sure that what we're writing for r and s will give us these roots for values of 0. So when I write these out, I just have to remember that I really need the opposite sign here. X plus 1 and x minus 4. So even though this is a negative 1, remember that's what x has to be for y to equal 0. So as long as x is negative 1, this works. It only works when r is plus 1. Same thing here. If I want negative 4 to show up for s, then that's because my root is positive 4, and 4 minus 4 will give me 0. Now from here, how do I find a? Because if I can find a, then I can solve the whole thing, right? I can make an equation out of this. And so in order to solve for a, I just need one other point on the graph that I can use, and then I can substitute it in, and we can solve an equation for this thing. So my equation, or my value, is right there. That's the one that I can see right away. That seems like it's pretty easy to use. So I can have a coordinate point here of 0, 12. And then I can see that I have x and y that I can plug into my equation. That will help me solve for a. So when x is 0 and y is 12, we're going to plug this in and see what this looks like. So 0 plus 1 and 0 minus 4. So 12 is equal to 0 plus 1 is 1, 0 minus 4 is minus 4. So it looks like a is equal to negative 3. So now once I write out my equation, I've found out what my stretch value is. That helps me write out the whole thing, and I can see that y is equal to negative 3, x plus 1, and x minus 4. And from there, we can solve for many different things, switching into different forms, telling different characteristics of the graph, and all that kind of stuff. So, in general, we've got a couple little things here, and these are just kind of more the note side of things. So when a quadratic function is written in factored form, it looks like that. Each factor can be used to determine a 0 by setting each factor equal to 0 and then solving it. And that's what we've been doing kind of throughout the whole thing. If a parabola has 1 or 2 x-intercepts, then the equation of the parabola can be written in factored form using the x-intercept and coordinates of the other point on the parabola. And quadratic functions without any zeros, they can be written in factored form. So just kind of some notes to take away from this stuff as well. And so these are kind of some things that you need to know. Factored form is written with ax minus r, x minus s, and it has the following characteristics, where the x-intercept of the graph of the function are r and s, and then the linear equation of the axis of symmetry is really just taking a look at those two roots, adding them together and dividing by 2. The y-intercept is always just c, where c is just equal to a times r times s if it's in factored form. If it's in our standard form, where it's ax squared plus bx plus c, all we do is just set x equal to 0, and then it's just our c value left over. So we can take a look here and see some different characteristics of graphs. And so things like the axis of symmetry, r plus s divided by 2. Finding our roots, just kind of making note that the y value has to equal 0 in order to find your roots for r and s. Our c value is found with the y-intercept when x is equal to 0. And then this thing opens upward as long as a is greater than 0. When a is less than 0, we can see it opens downward, and we have all of the same characteristics again for graphing this thing out. So all of a sudden there's a lot of different parts that we can take from this and use it to our advantage. If a quadratic function only has one x-intercept, and we ran into that problem earlier, the factored form can be written basically by taking these two together and just saying that they're squared. And so that just shows that there's only one root in the equation, where it only crosses the x-axis at one spot. So hopefully that was beneficial to go through and you learned a little bit. Let me know if you have any questions.